which helped me understand exactly what people are having issues with. Okay, so let's look at a couple of problems here. I think if you really, really plug into this, you're gonna come out feeling out at the end of the period feeling on top of all this stuff. Okay, so on this first one here, we're given a position, we're just gonna use a little physics here. We're given a position function, s of t, function of t, and we're gonna calculate velocity, which is just the derivative of s with respect to t. I'm gonna write it this way. Okay, we could also write it as s prime of t, right? So, easy, right? What do we get? 4t plus 3, right? Okay. Now, I want to give you a different function. Similar. This time I'm going to have a different situation, and we're going to say this time that velocity is equal to 2 times position cubed. Okay? And we want to calculate acceleration. Okay, what's acceleration? With respect to time. Okay, how do we do that?
So you have to do the v as. Like you have to do the v with respect to s. Yeah.
Okay, so right, so there's two parts to this, aren't there? Right? We've got at the outermost level, the 2 we can just leave out front, right? At the outermost level, we just have something cubed. What's the derivative of something cubed? 3 something squared, right? Okay, so we're going to get 3 times 2 is 6 times something squared, and the something is an s, right? Okay, but there's another layer to this, isn't there? If I look inside that function, I've got s. So then I have to differentiate s with respect to t also. That's the next link in my chain. So what is that? What's the derivative of s with respect to t?
18.
Just ds dt. We don't know, right? We don't know because we don't have, let's say these two are disconnected, right? So we don't know, this is a different problem than this one. In this case down here, am I ever given what s is as a function of t?
No.
I'm not, right? And so the best we can do about this at this point is just say ds dt, right? Now, if I had, let's say we knew, if I actually knew down here, if we plugged in, okay, I'm going to tell you that in addition to this stuff, we know that s of t is equal to, I don't know, 2t to the 4th plus 3t. Okay, now we could get somewhere, right? Now if I wanted to, I could find the value of, or I could find the acceleration function as a function of time, couldn't I?
Yeah.
Right, because all I would do,
Are you recording?
I am recording, yes. Right, because all I'd have to do now is take this function, this s function, s is now written in terms of t, and plug it in there, right?
Yep.
And that would give me 6 times the quantity 2t to the 4th plus 3 squared times, well, now that I have s of t, I could calculate s prime of t, same thing as ds dt, right? What would that be?
8t cubed plus 3.
8t cubed plus 3, right? And all I'd have to do there is just plug that in for that guy.
Okay.
And I would get 6 times s times ds dt, which is just some answer, right, in terms of t. Yes, sir?
You've got a t with a 3.
Say it again.
You've got to add the t with the 3.
Oh, I did. Right here, there should have been a t. Yep. Thank you.
And
Should have been a t there, shouldn't there?
8t cubed plus 2 or 3, because it's written differently.
Oh, you're. God, why can't I?
That's okay.
What is my problem here? I can't seem to get this stuff. So you're right. It's plus 3.
Okay.
Make sense? Okay, so we can't understand here that if I hadn't been given this, we would just be stuck with this answer. It's still the right answer, but we just can't fill in any more of the blanks, right? Okay, why didn't we do that up here for this problem? If we look down here at this, what we did, right? How come we didn't use the chain rule there? Or did we and just not even think about it? Kind of. Yeah, we could have, but it would have been superfluous for us to do that. If we tried to use the chain rule here, at the outermost level, I've just got some function of t, right? So if I differentiate this term by term, what's this first term going to be? Well, I'm going to get for the first term, if I tried to use the chain rule, what is the derivative of, I've just got 2 times something squared, right? What's the derivative of 2 times something squared? 4 times something, right? And the something is a t. And if I tried to use the chain rule there, it really doesn't get me anywhere, does it? Because now if I look inside and I take the derivative of t with respect to t, what do I get? 1. So the chain rule didn't really get me anywhere. I didn't need to do it, did I? I mean, technically, I guess I did. But it doesn't go anywhere, right? The only reason I would ever need to use the chain rule in a situation like this is if I were differentiating a variable with respect to a different variable, right? Does that make sense? Okay? In this case, because I'm differentiating t with respect to t, I'm done when I get there. There is no other layer for us to peel, really, is there? Think about that in terms of the other chain rule problems that we've done, the practice problems that we've done. If we had one like, let's just try this one. If we have the y equals sine of x squared plus 3. Let's calculate dy dx. So how many layers are there to this problem? 2, okay? So the outer layer is just a sine. Derivative of sine of hand is cosine of hand. Right? Hand turns out to be an x squared plus 3. Okay, so now I'll turn my attention to the next layer. What's the derivative of x squared plus 3?
2x.
Okay, 2x. And I don't need to go any further, do I? I could have said, I guess, that there are 3 layers to this function, but the third layer is just a waste of time. Because when I take the derivative of x, what am I going to get? Just 1, right?
Yeah.
So this one has, this is an important distinction. So this problem right here, if you get this, this is something. Now please pay attention. Don't get distracted. Ryan, turn around. So this one has 2 layers, right? Okay, compare that to this problem.
Mr. Oya?
Yeah.
How is that 2x down 1?
Say it again.
So we
You said
explained
the
that.
derivative of 2x is 1.
No, not the derivative of 2x. If I peel that layer again, right? So if I said, okay, I've got the derivative of sine of something, right? And that gave me cosine. If I look inside, I've got the derivative of something squared plus 3, which is 2 times something, right? But then the derivative of that final something would just be a 1. So we don't need that layer, do we?
No.
Right? So 2 layers was sufficient. Okay, but what about this one? What if I do instead the y equals sine of z squared plus 3, and I want to calculate dy dx. Now how many layers are there?
2?
No. Now there are 3.
Just with the change of a letter?
Here, yeah, you'll see why. Let's look at the layers.
Oh, because it's not, okay,
Ah,
because z isn't x.
Because z isn't x, right. So now watch how this happens. See how we get 3 out of this instead of 2. So at the outermost level, what do we got here?
Cosine.
We got sine, derivative of sine is cosine, right? So the first layer is going to be
Cosine.
cosine of hand. Okay, second layer is the, what do we got in here? The second layer, I've just got something squared plus 3. So what's that?
Times 2
something.
Okay, good. That's going to give me 2 times something, right? The something is a z. Okay, but now I need another layer. Because now if I look inside that one, what's the derivative of z with respect to x? dz dx, right? We don't know what that is. We don't know what that is, but it's something, right?
Why did you get rid of the
You don't know what g is.
Why did I get rid of the, say it again?
You get dy over dx, why did you get rid of the y? Yeah, why isn't it dy over dz? Yeah.
Okay, now listen, if I said, okay, that's a good question. So this is what we get if we take, here is my function, right?
Yeah.
And we calculated dy dx. Okay, let's do the same thing. The question is, why didn't we just take dy dz? And the answer is because that's something different. Let's calculate that. What is dy dz? So dy dz, same pattern, right? Outermost level is always just sine of hand. Well, the derivative of sine of hand is cosine of hand. Okay, next layer. What's the derivative of z squared plus 3 with respect to z? 2z, done,
How?
right?
Oh, because it's y.
Because the next layer would be 1. If I try to differentiate the next layer, which is derivative of z with respect to z, I get 1. So I don't need that layer, right? What's the difference?
Why dz over dx?
Say it again. Okay, because up here, I'm differentiating with respect to x, not z, right? So if I'm taking a derivative, a rate of change of this big function with respect to x,
It's like the multiple rate, like where it cancels out or something.
Oh.
say it again.
There's like the cross, like is it like crossing like the multiple bridge?
Well, it's,
Like changing the variable?
I mean, yeah, but you don't have to, but just think of it this way, right? I've got to have another rate of change there. In this guy right here, if I'm just trying to find the rate of change of y with respect to z, I really only need 2 layers to that, right? 2 layers. Because I've got the cosine of something, the sine of something that I'm going to have to differentiate, right? So I get the rate of change of sine of something is cosine of something, right? Next layer, I've got a z squared plus 3. Well, the rate of change of z squared plus 3 with respect to z is 2z, right? There's no other thing for me to do because the next layer would be dz, which is 1. Okay? Z is not changing with respect to itself, is it? Right? Okay, but look at this one. This is different. Now we're differentiating the same function with respect to x. That's a different variable, right? So we've got the rate of change of sine of something is just cosine of something. Peel the layer. The rate of change of something squared plus 3 is 2 times something. But when I look inside that one, what is being squared? Well, it's a z. The rate of change of z with respect to x is something maybe, right? Z might be changing with respect to x, right? They're different variables. So I have to include that last step. I don't know what it is at this point. I don't know presume that I am not given what z is as a function of x, and so I can't go any further, but if I did know, I could.
It's like
Right?
a U, it's like a
Exactly. It's just like when we have a u. Exactly. And that's, now let's look at some, any questions on that so far? Right? Okay, so everybody do one of these for practice, and then we're going to move on to something, kind of the next step. So try this.
So like, what would the wording be on this? Like, what would the question ask?
It'd ask you this, find, it'd be something like this. Let's say y equals sine squared of theta. Find dy dt.
How do you know there's not like 2 steps at the ends? Or is it always just gonna be 1 extra step?
It's gonna be one extra step because you're gonna have. So what Janelle's suggesting is how do you anticipate how many extra steps? It can only be 1 because, and we know there's gonna be an extra step here because we're differentiating this function of theta with respect to a different variable. So we know at the end we're gonna have to have a d theta dt pop out.
Is this on 2.4?
Yeah, this is all 2.4 stuff, yeah. Okay, so do that one for me real quick. You ready to take a look?
Yeah.
Okay. Okay, so first of all, what should I probably do to this function? How should I rewrite it to make the layers more obvious? Okay, good. So we're going to rewrite this as the quantity sine theta squared. So let's just follow the chain rule here. So what's our outermost layer?
But
No.
it becomes
Squared.
Oh,
Hand squared, right? Okay, so the derivative of this function with respect to, doesn't even matter at this point, right? With respect to t is just going to be outermost layer is the derivative of hand squared is,
Two something.
Two
cos.
good,
Oh.
2 hand, not cosine. We can't combine the lengths, right? The first layer is just 2 times hand to the 1, right? Okay, next layer. So over here, here's our box where we're peeling stuff away. So now what we've peeled away, so this step right here corresponds to this now, right? We've peeled away that first layer and differentiated it, right? Okay, so now we're to the next layer of the onion. The next layer is what? What kind of thing is it? It's a sine of something, right? So it's a sine hand. What's the derivative of sine hand? Cosine hand. Okay? So we get cosine hand. What does that do? That allows us to peel away, we just differentiated sine, so now we just dealt with the sine layer. Okay, what are we left with? Another layer, right? Because now we're differentiating theta with respect to t.
Delta.
And so this is gonna be, what's my last?
D
Theta dt.
And so would you literally write that in your answer?
Yes.
You'd write, so what you just wrote, would you input that into the answer box?
Yeah, yes, you would. If that question were being asked, that is exactly what you'd input. Okay, what's more likely to happen at this point, though, is you're likely to get that question, and what they're going to ask instead, they're going to give you some additional information. They're maybe going to say something like, okay, we know in this case that theta of t is, I don't know, it's the square root of t. Okay?
Oh, so you times it by the square root of t in your answer?
Okay, well, so every place I have a theta then, I could plug in a square root of t, right? Okay, so then they might also say, let's calculate this when t equals 1. Okay? So then, so yeah, that would give you then, would you agree that theta of 1 is equal to 1, right?
Yeah.
Okay, well, what is theta prime of t? Question?
I don't know. Wait, why does it equal theta? I'm so. T to the 1 half. Theta times 1 doesn't equal theta?
Theta of 1,
Oh.
right? Theta is a function of t, right? So this is a function. We're saying let's evaluate this when t equals 1.
Oh.
Okay, same thing, right? Okay, so we're evaluating when t equals 1. Well, what is d theta dt, if that's our function?
So that would be,
It's to the 1/2 power, right? We could rewrite this as t to the 1/2. So what's the derivative of t to the 1/2?
1/2
Yeah, 1/2 t to the minus 1/2, which we could, minus 1/2, which we could more conveniently write as 1 over 2 times the square root of t, right?
Right.
Because a t to the minus 1/2 is a t to the 1/2 on the bottom. Right?
Oh, yeah.
Okay, so then what is, we could also call this, if we wanted to, we could call this theta prime of t.
okay.
Same thing, right? Theta prime of t is the same thing as d theta dt, right? Everybody see that?
Yeah.
Those are just different notations for the same thing. So then what would theta prime of 1 be?
1/2.
Be 1/2, wouldn't it? Good, right? I'm just plugging in 1 for t. So then what if the question actually asked you, if it said, okay, well, find dy dt when t equals 1.
So it'd be 1/2.
Yeah, so then every place I have a theta, if I'm evaluating this when t equals 1, I'm just going to plug in a 1, right?
Oh.
Why wouldn't you plug in a half?
Because the half is theta prime. That's d theta dt.
So
Where
we
does the
need
1/2
to
go?
add it At the very
At the very
end.
end.
Yes.
Okay.
Good.
Sometimes it's so much under.
What?
right? Everybody see that? Yes.
So you,
Make sense? So my answer would be weird. What would my answer be? Somebody read back my answer to me then.
Y prime equals 2 5 sine 1.
Well, okay, sine 1 is just a number, right?
Yeah.
2 sine 1
Times
times
cosine.
cosine 1
Times a half?
times 1/2. So the 2's would cancel. Yep.
I would have never thought of that. I wouldn't have thought of it.
Is it the like f of u one? Okay, well, do you have it written? Do you want me to just pull up the assignment? Okay. Okay, back to business. Here we go. Back to business. Okay, questions? Okay, yeah.
So is this an example of like the U and?
Yeah, so let's look at one that's more like what you see on the assignment, maybe, right?
Okay.
Let's look at one like this. Here's the next step. Okay, you cannot get bogged down though. Don't get distracted. You gotta hold your train of thought 'cause this all connects.
Okay.
Okay, so let's take this guy. What if we have f equals u to the 7th, we'll even call it f of u, minus 8. Okay, and I want to find the derivative of this, right? If we were to call this y, let's say, if y equals f of u, which equals u to the 7th minus 8, I want you to calculate dy dx.
How does it become that?
Okay, so it's the same thing we just did, isn't it?
Yeah.
Right?
Let's do it.
Okay.
And this is with the chain function?
Yeah, it's gonna be the chain rule. Yeah.
And this question has 2 functions.
Yeah, it does. But I'm not gonna give that to you yet.
Oh, no, no.
Okay. So let's just maybe even do this one together. So what do we get?
yeah.
Okay, we're just gonna differentiate this term by term, right?
Yeah.
I've got 2 terms.
Yeah.
What's the derivative of u to the 7th? Yes, ma'am.
7u6.
Okay, so 7u to the 6th. Okay, but if I take that one more level, if I'm differentiating this first term, I'm gonna change this I'm gonna make this a u.
Oh,
Okay.
Pat, man.
And make that a u. Just because I think it'll make my point better. Okay, so that first term is going to give us. I've got to do the derivative of the first term completely before I move on to the second term, right?
Right.
Okay, so the derivative of u to the 7th is 7u to the 6th, but really that's what we really did there was we took the derivative of hand to the 7th, which was 7 hand to the 6th, right? What's the next layer of that? Times.
Times.
Don't ignore the second term. We're not there yet, right? First term, we're not done though. We're differentiating with respect to x. So the outermost layer is hand to the 7th. You already told me correctly that the derivative of hand to the 7th is 7 hand to the 6th, right? Okay, but I'm not done. If I peel away that outer layer, now I've got a u, is what was behind my hand. So what's the derivative of u? Ah, okay, it's not 1. It's not 1 because we're not differentiating with respect to u. We're differentiating with respect to x, and so du dx is something, right?
I get you.
Okay, so I've got to include
So we're times that.
a du dx.
Okay.
Yes.
So when we first started derivatives, then like our answer for that one would just be 7u6 minus 6 minus 8. That's because it was always x.
Exactly.
So
Exactly.
now we're doing it where it's a different.
Perfect. Okay, so if I had instead, everybody see this, if I had given you this problem, if I had said calculate dy du, that would have been easier in a way, right? Because then I would have only had one layer, right? When I differentiate that first term, I would have gotten 7u to the 6th, and then the du is just 1. There is no other derivative, right?
Yes.
Okay?
But then would you just, if it was that, then would you say times negative?
No, not times. Now we're just going to finish the derivative. We did the first term. Recall that when we differentiate a string of terms, thankfully we get to just differentiate the terms one at a time. That makes things much easier. That's easier than like the product or the quotient rule, right? When we've got a sum of terms, like a polynomial, we could just differentiate each one by itself and then combine the answers to be our derivative, right? So we're done with this one, now we move on to the next one. What's the derivative of 8 times hand? 8. Okay, so then we're gonna get a,
Wouldn't it be negative?
oh, so minus 8, right, minus 8.
Wait, times that.
No. No, because look, that's a minus sign.
Oh.
Okay, now you answer your own question here. If I had y equals 3x cubed minus 7x squared plus 3x, what's dy dx?
9x squared minus 14x plus 3.
Well, don't I multiply those? No, I don't, right? I differentiate term by term. I take the derivative of this one minus the derivative of that one plus the derivative of that one, right?
The other one is multiplied because of that extra part.
Right? Okay, so why was this multiplied? Because that was a part of the derivative of the first term, right? All of this stuff right here, all of this stuff is linked to that, right? Okay, what about the derivative of the next term? So now we're focusing on this guy. Well, the derivative of 8 times hand is just 8. But when I peel my hand away, we see that what's behind my hand is a u, and the derivative of u with respect to x is
du
du dx.
Should we like make du dx squared?
No? Okay, now hold on. This is gonna be, this is big. This is gonna be an aha moment for you. Okay, so now if I wanted to do a little algebra here, is there something I could factor out?
Yeah.
A du dx, what do you know? So my answer looks like, hang on, watch. So it looks like 7u to the 6th minus 8 times du dx.
Wait.
Right, so I factored that out.
I feel you.
Okay, got it? Okay, now look at this. Isn't this the very same thing then as saying dy, whoops. How's it going? Oh, way down on me. Here we go. So isn't this the very same thing as saying dy dx equals dy du times du dx?
Yeah.
Right? Now let's look. Is it not?
Yeah.
If I started with, remember what we just said, if we started with dy du, we wouldn't have needed that, would we?
No.
Right?
Right.
Would you agree that dy, don't talk, look up here please. Would you agree that dy du is just gonna be 7u to the 6th minus 8? Yeah, right? That's it. Okay, so there's my 7u to the 6th minus 8. That's my dy du times, I need a du dx there though, by the chain rule. Right? dy dx would have to equal dy du times du dx, so those du's could cancel, right? There's my du dx. Isn't that cool? Right? So practically speaking, we really have two ways of doing this, don't we?
Yeah. See, we have the easy one.
Well, I mean, no, that is the easy way. Yeah.
Wait, so it's
We
not,
just did the easy way.
so it's just
Oh,
dy
let's take it
over
easy.
dx?
Yeah.
But then how is,
Right, so we could have, you see what I'm saying here is that we could have, what we chose to do was we just differentiated directly with respect to x, right? And so we had to apply the chain rule twice here. To each term, we had to have a du dx pop out, right? Okay?
Yes.
Well, do you see that if we had a whole bunch of terms, that might be a little bit cumbersome to have to rewrite that du dx in each term, correct? So instead, we could just think of this from the beginning as a big chain rule problem, right? We know that dy dx just equals dy du, which is a pretty easy thing to calculate because all my terms had u's in them instead of x's, right? Times, at the very end, I'm going to have a du dx, which is multiplied by each term in that derivative, which we got anyway if we just factored those out, right? So try one of these now. I'm going to give you a hard one. This is like one that you do on one of your problems. do this one.
Mr. Oil,
Yeah.
so what was the answer for that last?
Okay, so the answer, the answer is
Wait, could you,
Never mind.
that.
wait,
But wouldn't it just be
Just
dy over dx?
No.
Would it be dy over dx? Because that's what's left.
Okay, this is the answer.
Yes.
Now, on the assignment that you got, you were told what u was in terms of x, and you were told what the value of x was, right? So yours, in a way, was even a little bit harder, because yours said something like this. Yours would have said u equals
I have one.
g of x equals like,
Square root of x.
or we did square root of x last time, right?
No, you didn't. 3 square root of x.
Oh, okay, well, we can just do square root of x then, that's fine. Right? So if u equals the square root of x, then du dx equals what? Would you agree it's just 1 over 2 times the square root of x? And what if they told us furthermore that we're going to evaluate this when x equals 4?
Then that
Plug
would
in the
be
4.
So what would the value of u be?
1/4. Boom.
Yeah, then u would equal 2, right? Square root of 4. And du dx would equal 1 over 2 times 2 is 1/4. So I could just plug those in. Every place I have a u, I could plug in a 2. Every place I have a du dx, I could plug in a 1/4 and get a numerical answer, right?
I don't like
Right.
that as much.
Yeah, I know, but that's what you're gonna do on the assignment though, right? It's no big deal, right? It doesn't really make it that much harder, but this was your answer. This was your general answer without plugging in something specific.
But what if
Okay.
they give you an equation?
What do you mean?
Like the f of u, like the thing you have.
Okay, so let's do one of those.
Okay.
So if they give you one like this, if they say, let's say we get okay, and it's not, we could just call it u of x, couldn't we? Yeah. So there's a problem like you might do, okay? You're asked to find, what you're asked to find here is,
Don't plug it in until later.
right. Okay, so, up here. So what about this then? I'm trying to find the derivative of the composition, right?
Uh-huh.
Isn't that the same thing as calculating f prime of u times u prime, u dx? Right? That's what this means. We could write this in two ways. I could write the whole thing as f of g of x, right?
Yes.
Okay. Oh my gosh. Right, I could call that y. Y equals f of g of x, right? And I'm trying to find y prime. So by the chain rule, isn't y prime just f prime of, what is that in the middle? That's just a u, right? So that's f prime of u times u prime, du dx. Right? Okay, another way of saying that would be y prime is the same thing as saying dy du times du dx, right? Okay, either way though, we made this easier in a sense because you're given the function of u, right? So whether I call it f prime of u or dy du, that's not going to be hard to do. It's a product rule problem if we don't, and assume that we don't multiply it out and expand it first. So, would you agree then that f prime of u is equal to, oops, I got it, first times derivative of the second, which is what?
2u.
And I'm differentiating with respect to u, so I don't need anything else, right? I'm done. Plus the second
2u.
No, just u squared.
times the derivative of the first, which is 8u, right? So there's f prime of u, okay? That's what goes there. Now what about the u prime? Well, they tell me what u is. U is that.
So we just need to find prime of it.
Yeah. So du dx is what?
8 at 8x plus 7.
Good. Okay. 8x plus 7, right? And so now my answer is just going to look like that times that, right?
Wow.
Make sense?
Wow. Wait, will you tell me I was right?
Okay. So my answer, y prime, just looks like f prime of u, or dy du, same thing, which is this stuff, times u prime, or du dx, which is that stuff, right?
Where would you plug the x equals 0?
Okay, so now that's, the x equals 0, keep in mind that that's just one specific example of the infinite number of choices we could have for x, right? So what we're saying here is, okay, we're going to calculate this general derivative that's a function of x. Our derivative is, if I combine all this stuff here, right, the derivative is f prime of u times u prime. Well, that's that thing. So y prime equals this guy. And we could make that even a little simpler if we want to. What's 2u times 4u squared?
8u squared.
8u cubed plus, what about here if I distribute
8u cubed plus 48u. I mean 40.
40u? Okay, and I could even make that a little bit simpler. I could make that instead.
But do you have to simplify it?
No, you don't.
I like simplifying. Wait, but what are we doing this for? What is
Okay.
it? Why?
Okay, hold on. That's because focus. So that's just this part, right?
Yeah.
Okay, times that part.
Times 8x plus 7.
Okay, so that is,
Your answer.
okay, yeah, kind of, right? That's my general answer. And if I wanted to go a step further, this would be really messy. This would be really messy, but we don't have to do it. We don't have to do it. I could plug in, here is u, right, as a function of x. So if I wanted to write this whole function of x, I could, this would be horrible, but I could plug in that polynomial
Oh no.
right there and cube it, and right there,
Oh, yeah.
right? Yeah.
Can you, just go back up for a second?
Other,
So like, can you plug x in, like 0 into that equation, and you get 3, and then you plug u equals 3?
okay, yes, but that's just because of the one particular question that happened to be asked of you, right? What this was saying was, okay, we're going to cut you some slack here because instead of having to write out this whole function of x, all we really want to know is what is the value of the derivative when x is 0. But what if we needed more than that? What if we actually needed the general function and we wanted to be able to calculate the value of the derivative when x equals 10 or pi or negative 100 or whatever, right? Okay, then our answer would be that, right? This is dy dx.
So that could be your answer in your math exam.
Well, no, you don't have to, because on your assignment, you're not being asked this. But I want you guys to understand. I don't want you to draw the conclusion that's an important part of the question. That's a intrinsic part of the question. It's not. They're saying, okay, find the derivative, but then just evaluate it when x is 0, right? Most of the time, we're not going to do that. Most of the time, we want to find the derivative function and do something with it. Yes.
So you would just plug 0 in for the 8x plus 7?
Okay, so what we would have to do then, now, if we're going to evaluate this when x equals 0, then we're going to figure out we're gonna figure out what is the value of u when x is 0, which we could do, just plug it in, right? When x is 0, isn't u equal to 3,
Yeah.
right?
Okay.
And isn't u prime just equal to 7,
Yeah.
right? So we could have gone clear back here and just said, okay, well, we get 16 times 3 cubed plus 40 times 3 times 7, right?
Yeah.
And that's gonna be my numerical answer. Agree?
Why is u prime 7?
Because
Zero.
when x is 0, doesn't that become 7,
0?
Yes, it does.
right? Okay, make sense?
Yes.
Can we
Okay.
do a work day tomorrow? Yeah.
Yeah, I don't think we're done though. I think we gotta do, I'm not convinced that everybody is 100% on this. So I'll give you a work day, but we're gonna do one more example.